Here's a simple circuit you can look at with the oscilloscope. This is as I said, it's a simple RC circuit. Basically, I have my signal, and we'll look at DC and time-varying signals, going through a 150 kilo ohm resistor, and then there's a 0.01 microfarad capacitor going to ground. And the capacitor, the simple way to think of it, is just two metal plates that are separated by an insulating material. So if you just have a simple DC voltage, it can't get through the capacitor, so this will act like an open circuit. So at DC, it'll just go straight through the resistor, and you'll see the DC go there. For low frequencies, it's somewhat similar. It'll mostly just go through the resistor, and very little will go through the capacitor. And so you'll see the signal that you put through mostly on this side. As you increase the frequency, the little wiggles in voltage can induce wiggles in voltage on the other side through the insulating material. And so if you get the frequency high enough, the electricity basically takes the shortest route to ground and goes all through the capacitor. So if you're looking at the signal here at very high frequency, you don't see anything. So essentially this is a low-pass circuit. And some measures, some figures of interest are the RC constant, which is 1.5 milliseconds, and I show you the math, and then the minus 3 dB frequency, which is approximately 100 hertz. So what we'll see is that at low frequencies we can see the capacitor charging, and we'll see a characteristic time of that is 1.5 milliseconds. And if we look on it at a frequency-dependent level, we'll see that it'll pass frequencies around the 100 hertz level, but if you go much higher than that, it starts shunting them to ground, and you see less and less of it. So I have this, let's get this all worked out here. Hopefully that's visible. I'm going to have to check this again to see if I can actually see things here. It's kind of hard to tell what'll be fuzzy and what won't. So right now I'm passing a DC signal through it. So if we look at the signal that I'm passing in red, it's right there, and then the signal that's coming out is in blue, and it's right on top. So at DC, we see it going straight through. If I now put in a sine wave, like a short sine wave, we see that it's mostly the same, and I should turn the triggering on so it'll stop moving like that. So there's the output, and there's the input, and they're very, very similar. One thing you can do at this low frequency is look at a square wave. And again, it looks pretty close. But if you start blowing it up and go to larger and larger times, you will see that whereas the signal comes pretty, the signal that you're feeding in comes in pretty sharp, there's a characteristic time for the capacitor to charge up to that level. And that was the RC, the 1.5 milliseconds that we were looking at before. So what you can do is you can take a look at the, right now the difference between the top and the bottom is 2.63 volts. And if we look at what 63% of that is, it's about 1.65. So if I move this cursor down to 1.65, that's pretty close. And then I look at the characteristic time it takes for it to charge up to the level, we should see that it comes out to be about 1.5 milliseconds. And I'm slightly off, it's varying a little bit. But basically, now that I've gotten to that point on the curve where it's going to 63% of its voltage, the characteristic time is 1.54 milliseconds, and that's pretty close. That's within the tolerance of the capacitor and resistors. They're not exactly 150K and 10 to the minus 8 farads. There's slight variations, so that's why that's off a little bit. So that's one thing you can do with it. The other thing that you can do is you can go to the circuit analyzer function here, and we know that the characteristic frequency is about 100 Hertz from our calculations, so we'll go up to 10 kilohertz, and we'll look at this, and we'll let the frequency analyzer show the behavior of the circuit at various frequencies. So you can see starting off, it does pretty well, and then it drops as the frequency goes up. Right now we're at 100 Hertz, and as you keep increasing the frequency, the signal that you get out at the end goes lower and lower and lower and lower as the capacitor shorts more and more of the electricity to ground at higher frequencies. So now what we want to do is we want to figure out the F3dB point. So we mark the beginning level, and then we look at where we are 3 dB off, and I just got to it right there. That's 3 dB. And so let's look at where that intersects the curve. And if we look, that's 99.1 Hertz, which is very, very close to our 100 Hertz level. So we can see that with this oscilloscope, we can measure various things about this circuit pretty accurately. And just to give you an idea of what happens, so we've, you can actually see. So if we go from, let's choose 5 Hertz, and go on a better time scale here. So they're right on top of each other, which is why you can't see it very well, but basically at 5 Hertz it accurately reproduces it. If we go to 50 Hertz, it's still pretty good because we're very close to the F3dB point. If we continue to increase it to 500 Hertz, it's hard to see, but the red you can see pretty easily. Yeah, there you go. You can see the red very easily. That's the input signal, and you can see how severely attenuated the blue signal is. And so that's almost, that's 5 times the F3dB point. If we keep increasing it, eventually it'll turn into a straight line. Oops, I don't know why I did that. I think it just got confused. Sometimes it does that. Basically, we're kind of seeing a straight line here. There we go. That's what I wanted. Sometimes you have to play with it a little bit. But basically, you see the input signal and how there's almost no variation now in the output signal. And it'll just get worse and worse as you go on. So, that's the first part of playing with an RC circuit.